Now let's talk about magnetism and current carrying wires. We know a moving charge causes a magnetic field. So what about when you have a bunch of moving charges, like in a current? Well, by convention, um, we're going to let's look at some directions. If the magnetic field is into the page, we're going to make an X, okay? If the magnetic field is out of the page, we're going to put dots, okay? They're either circles or dots. Sometimes we do circles with little dots in the center, okay? Or just solid dots. Think of an arrow, okay? The tail of an arrow looks like a little X, while the head of the arrow, if it's heading towards your face, is going to, be the circle with this little dot. So, if I have a current that's flowing out of the paper here, you're going to make a circle with a little dot. And if you have a current that is going, magnetic field going into the paper, so in this case the current is flowing into the paper, then you make an X. So, into the paper, X, out of paper, dot. It doesn't matter whether it's a magnetic field or current or force or whatever. This is just a standard convention. Now, suppose we have a charge moving in a magnetic field with a velocity perpendicular to v. It travels in a circle. Okay, think about this right here, and I wish you could see my hand. Stick your thumb in the direction of the velocity, all right? In this case, a magnetic field is into the page, all right? So B is into page, all right? So put your fingers into the page, and then this is your thumb. All right, you'll see your palm, okay, faces in. Well, if that's the direction of the force, and you move up, it's going to scooch a little bit. All right, so now the velocity is perpendicular. The B is still into the page, and so you have a force going to the circle, to the center. So you see, you create this circular path if your charge is positive. So if your charge is positive, all right, it's going to do a circle in this way. This is clockwise or counterclockwise? Counterclockwise. Now suppose it's negative. Your thumb points up, and because that's the velocity, your fingers point in, and the force is going to be out the back of your hand, so the force is going to be back. So as it moves up, it's going to be pulled in, and so you wind up with a force pulling you into a clockwise circle this way. All right, so if your charge is negative, it's going to move in a counterclockwise circle, while if your charge is positive, it's going to move into a clockwise circle. Now, electric currents and magnetic fields. Whenever you have moving charges, you produce magnetic fields. And the converse of that is true. Moving charges produce magnetic fields. So let's look at a wire traveling out of a piece of paper. So take your thumb and put it in the direction of the current. So your thumb is always going to go along the wire and then grab the wire with your hand. All right, the magnetic field is going to make circles around the wire. Now, what direction is the force? The force is going to be in here. It's always going to be facing the wire. And if you reverse the direction, of course, the magnetic field will reverse direction. This is just an example of how we draw the magnetic field around a wire. In this case, the current is going up. So this is your current, so put your thumb going up. And when you grab the wire, you see here it's coming out of the page and on the left side, and it's going into the page on the right side. If you just curl your fingers on around, you'll see on the back side they're coming out, and then they curl around the wire, and then they go into the page. So the magnetic field looks something like this for a current going up. If the current's going down, you put your thumb going down, and then it switches sides. So the magnetic field is going into the page on the left side and out of the page on the right side. Now, what is the magnetic force on a current carrying wire? Well, it's ILB, Philb, where FB is the magnetic force in newtons, I is your current in amps. Well, this is an amps, not an L. Length of the wire is M, and the magnetic field strength is in Teslas. Now, this is only true when they're perpendicular, but we're only going to do perpendiculars. Now, in this case, are they perpendicular? B is into the page, and I is up at this angle. Is B perpendicular to the current? And the answer is yes, it is. Because anything in this plane is going to be perpendicular to B, which is going in and out of the plane. So you have to be kind of careful with these. The right-hand rule for force on a current carrying conduction is very straightforward. We've already gone through it. Put your thumb in the direction of the current, and the magnetic field will make concentric circles around. And the palm of the hand, of course, is the direction of force, which will be toward the wire. This is a summary of the right-hand rule for current carrying wire and for a charged particle moving. You'll see QV and IL are equivalent. So FB is always the palm. There is no direction of the length of the wire. You're looking at the direction of the current and the direction of the velocity of the charge. Those are both going to be your thumb. And the magnetic field strength is always your fingers. Now, what if you have two current carrying wires? What happens when you bring them close together? Let's look at an MIT demonstration of what happens. Now, what we're going to do is we're going to flip the switch on and start a current in these two parallel wires. Now, watch what happens. All right. In this case, they're going in opposite directions. All right. And you see the wires are pushing themselves apart. Let's look at that again. All right. These electrons are going up, these are going down, and they push away from each other. What if they're going in the same direction? Okay. In this case, they wind up being attracted to each other. Kind of didn't expect that, did you? I always have to think about it. Think of it like this. If you're walking down the hall with your boyfriend or girlfriend, someone you're attracted to, you're going to get closer. But if you see somebody you don't like, you're going to want to, go away from them. You're going to go down the opposite direction in the hall.